Pick up any object within reach, a phone, a glass, a coin, hold it and feel the resistance it offers, the solidity, the weight, the way it pushes back against your hand with a firmness that seems to confirm its reality as a thing occupying space. That firmness is the most familiar physical sensation in human experience. It is also one of the most misleading. The object in your hand is almost entirely empty space. Not mostly empty in the way a loosely packed box is mostly empty, with identifiable gaps between solid pieces. Empty in a more fundamental sense. The atoms composing the object are themselves almost entirely empty. The nucleus of a hydrogen atom is roughly 100,000 times smaller than the atom itself. If you enlarged a hydrogen atom to the size of a football stadium, the nucleus would be a marble sitting at the center, and the single electron would be somewhere in the upper tiers of the seating. Everything between them is space, and yet the object does not pass through your hand. The Pauli exclusion principle operating on electrons creates a resistance to compression that produces the sensation of solidity. The firmness you feel is quantum mechanical in origin, not the contact of solid pieces, but the universe refusing to let electrons share the same quantum state. But that is not where this descent ends. It is where it begins. Because the nucleus sitting at the center of that stadium is not the bottom of the structure, the marble is not fundamental. It is itself a composite object. A proton and some neutrons bound together, each of which contains smaller constituents whose existence was not confirmed until the second half of the 20th century. Constituents that have never been observed in isolation, that may not be observable in isolation by any instrument ever built, and whose own internal structure, if they have one, sits at a scale current physics cannot reach. Those constituents are quarks, and the question of what a quark is made of is not a simple extension of the same logic that took physics from atom to nucleus to quark. It is a question that runs into walls those earlier descents did not encounter. Walls built not from experimental difficulty, but from the structure of the physics itself, from what it means to be confined, from what point-like actually means at quantum mechanical scales, from the energy required to probe structure smaller than anything currently accessible. The descent into matter has a history, and that history is the only honest way to approach the question of what sits beneath the quark, because every time physics declared it had found the bottom turned out to have a basement, and every time a basement was found, the tools required to find the next level down had to be rebuilt from scratch. Whether that pattern continues below the quark is one of the genuinely open questions in fundamental physics. Not open in the sense of awaiting a calculation, open in the sense that the experimental access required to answer it does not currently exist, and may not exist for generations. What does it actually mean for a particle to be point-like at quantum mechanical scales? Why has no one ever seen a free quark despite decades of trying? And if quarks do have internal structure, what would the physics of that structure even look like? If you like exploring questions like these, feel free to leave a like and subscribe. And if there is something about the universe you find yourself wondering about now and then, let us know in the comments. It might become the next question we explore. For now, let's get back to that question. The descent begins not with quarks, but with the object that was once considered the indivisible constituent of all matter, the atom, and with the moment that assumption was first cracked open. The word atom comes from the ancient Greek atomos, indivisible. The philosophers who coined it were not doing experimental physics. They were doing something closer to logical reasoning about the nature of matter. If you take any substance and divide it in half, then divide the half, then divide the quarter, can that process continue forever? Or does it eventually reach a piece so small it cannot be divided further? The atomists argued for the latter. Matter must have a bottom, a smallest piece, something that division cannot reach. They were right that matter has structure at small scales. They were wrong about where the bottom is. For most of human history, the atom remained a philosophical concept rather than a physical one. It was not until the 19th century that the evidence for actual atoms began accumulating in a form scientists could not dismiss. The ratios in which elements combined chemically were too clean to be coincidental. Hydrogen and oxygen always combined in the same proportions to form water. Carbon and oxygen in fixed ratios to form carbon dioxide. John Dalton proposed in 1803 that these fixed ratios made sense if each element was composed of identical indivisible particles with characteristic masses, atoms. The picture that emerged over the following century was of a universe built from roughly 90 naturally occurring types of atoms, each element its own type, each type indivisible and fundamental. The periodic table organized them by their properties and revealed patterns suggesting some deeper order, but the atoms themselves were treated as the bottom of the structure, the indivisible constituents of all matter, the point at which division stopped. That picture lasted almost exactly 1 century before it cracked. In 1897, J.J. Thomson fired electrical discharges through evacuated glass tubes and found that something was being emitted from the metal electrodes that was not light and not any known particle. Whatever it was deflected by magnetic fields in a way that indicated it carried negative electric charge. Its mass was roughly 2,000 times smaller than the lightest atom. It was the same regardless of what metal the electrode was made from or what gas remained in the tube. Thomson had found the electron, a particle smaller than any atom, a particle that came out of atoms. The atom was not indivisible, it had parts, and if it had parts, then it had internal structure, and if it had internal structure, then the question of what it was made of was suddenly not philosophical, but experimental. The immediate question was how the parts were arranged. Thomson proposed what became known as the plum pudding model. Electrons embedded in a diffuse positive charge like raisins in a pudding. A reasonable first guess given the available evidence. It was wrong in almost every detail. Ernest Rutherford dismantled it in 1909 with an experiment so simple in conception and so shocking in result that it became one of the defining moments in the history of physics. He fired positively charged particles at a thin sheet of gold foil and placed detectors around it to see where they went. Most passed straight through, a small fraction deflected at large angles, an even smaller fraction bounced almost directly backward. On the plum pudding model, large deflections were impossible. The positive charge was spread too diffusely to produce them. Rutherford later described his reaction as like firing artillery shells at tissue paper and having them bounce back. The only explanation was that almost all the mass of the atom was concentrated in an extremely small central region, a nucleus, tiny compared to the atom as a whole, dense enough to deflect fast-moving particles through large angles on close approach. The atom had a structure, a dense nucleus surrounded by orbiting electrons with almost nothing between them. The indivisible unit of matter turned out to be mostly empty space with a hard center, and that hard center was itself a new mystery. What was it made of? What held it together despite the electromagnetic repulsion of its positively charged constituents? And was it, unlike the atom it sat inside, actually fundamental? It was not. The nucleus resisted understanding for longer than the atom did. Rutherford identified the proton in 1917, a positively charged particle inside the nucleus. Hydrogen had 1, helium had 2. The charge of the nucleus matched the number of protons it contained, but the mass did not. Helium had twice the charge of hydrogen, but 4 times the mass. Something else was in there carrying mass without charge. James Chadwick found it in 1932, the neutron, a particle almost identical in mass to the proton but electrically neutral. The nucleus was protons and neutrons bound together. The periodic table suddenly made sense at a deeper level. Each element defined by its number of protons, each isotope defined by its number of neutrons. But a new problem immediately appeared. Protons carry positive electric charge. Positive charges repel each other. A nucleus containing multiple protons packed into an extraordinarily small volume should fly apart instantly under electromagnetic repulsion. Something was holding it together with a force strong enough to overcome that repulsion at short range. A force nobody had previously identified because it operated only at scales smaller than an atom. That force was the strong nuclear force, and it was the first indication that the nucleus was not just a collection of protons and neutrons sitting passively together. It was a dynamical system governed by a new kind of interaction with its own rules and its own complexity. The complexity deepened rapidly. Particle accelerators built in the 1950s and 1960s began smashing protons together at increasing energies. The collisions produced not just protons and neutrons, but a proliferating zoo of new particles: pions, kaons, lambda particles, sigma particles, dozens of distinct objects, each with their own mass and charge and lifetime. The particle zoo, as it became known, was theoretically incoherent. No framework could explain why these specific particles existed and not others, why they had the masses they had, what principle organized them. The answer, when it came, did not simplify the zoo. It explained it by revealing that every particle in it was composite, built from smaller constituents, and those constituents were quarks. The quark was proposed theoretically before it was confirmed experimentally. In 1964, Murray Gell-Mann and George Zweig independently proposed that the proliferating zoo of strongly interacting particles could be organized and explained if each particle was composed of smaller constituents. Gell-Mann called them quarks. The name came from a line in James Joyce's Finnegan's Wake, 3 quarks for muster mark, an arbitrary choice of name for something whose physical reality was far from certain at the time. The proposal was not immediately accepted. Quarks were a mathematical device that organized the particle zoo elegantly. But elegant mathematics is not the same as physical reality. The question was whether quarks were actual constituents of protons and neutrons, or simply a bookkeeping tool with no deeper physical meaning. The experimental confirmation came in 1968 at the Stanford Linear Accelerator Center. Physicists fired high-energy electrons at protons and measured how the electrons scattered. At low energies, the proton behaved like a smooth object. The electrons deflected gently and uniformly, as if hitting a diffuse cloud of charge. At high energies, something different happened. Some electrons deflected at large angles, the same signature Rutherford had seen when he fired particles at gold foil and found the nucleus. The proton was not smooth. It had hard, point-like constituents inside it. The scattering pattern matched precisely what you would expect if the proton contained 3 smaller objects, each carrying a fraction of its charge. The quarks were real. Subsequent experiments confirmed the picture in detail. The proton contains 2 up quarks and 1 down quark. The neutron contains 1 up quark and 2 down quarks. The up quark carries an electric charge of positive 2/3. The down quark carries a charge of negative 1/3. The charges of the constituent quarks sum to the charge of the composite particle exactly. The mathematics was not just a bookkeeping device, it was describing something physically present inside the proton. The particle zoo was suddenly comprehensible. Every strongly interacting particle was a combination of quarks. Mesons were quark-anti-quark pairs, baryons were 3 quark combinations. The specific particles that existed and the ones that did not were determined by which quark combinations the strong force permitted. The zoo had a grammar, and the grammar was written in quarks. Every step in the descent from atom to nucleus to proton produced free particles. Thomson's electrons could be isolated, stored, and studied individually. Rutherford's nucleus could be separated from its electrons. Protons and neutrons could be extracted from nuclei and examined in isolation. Each level of structure revealed constituents that could, in principle, be pulled free from the composite object containing them. Quarks cannot. No experiment in the history of physics has ever detected a free quark. Not a quark moving through a detector unattached to other quarks. Not a quark momentarily separated from its partners before recombining. Not a quark at any detectable distance from the composite particle it inhabits. The experiments that revealed quarks did so indirectly, through the scattering patterns of electrons bouncing off something hard inside the proton. The quarks themselves never emerged. This is not a limitation of the experiments. It is a property of the strong force. The strong force does not weaken with distance the way the electromagnetic force does. Pull 2 quarks apart, and the force between them stays roughly constant. The energy stored in the field between them grows as the separation increases. At some point, that energy becomes large enough to do something remarkable. It spontaneously produces a new quark-anti-quark pair from the field itself. The energy that was going into separating the original quarks instead creates new quarks that immediately bind with the ones being pulled apart. You started with 1 quark trying to escape and ended with 2 bound pairs. The quark you were trying to free is still bound. It will always be bound. This is confinement, and it means that quarks exist only inside composite particles, never alone, never free, never directly observable as isolated objects. Confinement makes the question of quark structure uniquely difficult. To probe the internal structure of an electron, you fire something at it and measure how the projectile scatters. To probe the internal structure of a proton, you do the same thing and find quarks inside. To probe the internal structure of a quark, you would need to fire something at an isolated quark. But isolated quarks do not exist. The very tool the previous descent relied on is unavailable here. Before the question of what quarks are made of can be approached honestly, what quarks actually are needs to be established completely, because quarks are not all the same. There are 6 of them, each distinct, each with its own mass and its own properties, and the differences between them are not small variations on a single theme. They span a range so vast it demands explanation. The 6 quarks are organized into 3 pairs, up and down, charm and strange, top and bottom. Each pair is called a generation. The up and down quarks are the lightest and the most common. They are the constituents of protons and neutrons and therefore of all ordinary matter. The charm and strange quarks are heavier. They appear in short-lived particles produced in high-energy collisions and decay rapidly into lighter quarks. The top and bottom quarks are heavier still. The top quark is the most massive fundamental particle ever detected, roughly as heavy as an atom of tungsten despite being a point-like constituent of matter. The mass range across the 6 quarks is extraordinary. The up quark has a mass of roughly 2 mega-electron-volts. The top quark has a mass of roughly 173,000 mega-electron-volts. a factor of nearly 100,000 between the lightest and heaviest member of the same family of particles. Why the 6 quarks have the masses they do is one of the unsolved problems of the Standard Model. The masses are not predicted by the theory. They are measured experimentally and inserted as parameters. The Standard Model accommodates them, but does not explain them. Where the mass hierarchy comes from, why there are 3 generations rather than 2 or 4, why the top quark is so extraordinarily heavy compared to the up quark, are questions the Standard Model leaves unanswered. This unexplained structure is one of the reasons physicists suspect quarks may not be the final level. A truly fundamental particle with no internal structure and no deeper explanation for its properties is expected to have those properties for a reason the theory itself provides. The Standard Model does not provide that reason for quark masses. It simply measures them and moves on. Electric charge is familiar. Positive and negative. Opposite charges attract. Like charges repel. The electromagnetic force governs the interaction between charged objects, and its rules are simple enough to be taught in introductory physics. Quarks have electric charge, but they have another property that has no analogue in ordinary experience and no connection to the colour of visible light, despite the name physicists gave it: colour charge. There are 3 varieties of colour charge. Physicists call them red, green and blue. These are labels, not descriptions. A quark carrying red colour charge looks no different from a quark carrying blue colour charge in any visual sense. The names were chosen because of a mathematical analogy with how the 3 primary colours of light combine to produce white. 3 colour charges combining in the right way produce a colour-neutral object. Just as red, green and blue light combine to produce white light, every quark carries one of the 3 colour charges. Every antiquark carries one of 3 anti-colour charges. The strong force acts between particles carrying colour charge, the way the electromagnetic force acts between particles carrying electric charge, but with a crucial difference. The strong force only permits certain colour combinations to exist as stable composite objects. Specifically, it requires composite particles to be colour neutral. A proton contains 1 red, 1 green, and 1 blue quark. The 3 colours combine to produce a colour-neutral object. A meson contains a quark and an antiquark, carrying matching colour and anti-colour charges. Again, colour-neutral. No composite particle carrying net colour charge has ever been observed. The strong force confines colour charge inside colour-neutral objects, the way confinement traps quarks inside composite particles. Colour charge is not incidental to the structure of quarks. It is the property that determines how quarks interact and why they cannot exist in isolation. Understanding what a quark is made of requires understanding what colour charge is at a deeper level. Whether it is a fundamental property of a truly elementary object or a consequence of some internal structure that generates it remains an open question. Colour charge would be an interesting but static property if nothing responded to it. What makes it physically consequential is the particle that mediates the interaction between colour-charged objects, the gluon, the boson of the strong force, the carrier of the interaction that holds quarks inside protons and holds protons inside nuclei and ultimately holds together every atom in the observable universe. Gluons are massless. They travel at the speed of light. There are 8 distinct types distinguished by the colour charge combinations they carry, and unlike the photon, which mediates the electromagnetic force but carries no electric charge itself, gluons carry colour charge. This single difference between the photon and the gluon produces consequences that reshape the entire behaviour of the strong force. A photon does not interact with other photons. 2 beams of light pass through each other without deflection because the electromagnetic field carries no electric charge, and photons do not couple to each other directly. The strong force field carries color charge. Gluons interact with other gluons. The field that mediates the strong force is itself subject to the strong force. The consequence is the flux tube described in an earlier script. The strong force field between two quarks does not spread outward in all directions the way the electromagnetic field does. It is pulled into a narrow, concentrated tube by the self-interaction of the gluons within it. That tube maintains roughly constant tension regardless of separation, hence confinement, hence the impossibility of isolating a free quark. But gluons do something else inside the proton that is relevant to the question of quark structure. They are not static mediators sitting passively between quarks. They are continuously being exchanged. Quarks emit and absorb gluons constantly. The interior of a proton is a dynamic churning environment of quarks exchanging gluons, and gluons briefly splitting into quark-anti-quark pairs before recombining. The three valence quarks that define the proton's identity, 2 up quarks and 1 down quark, are surrounded at any moment by a sea of virtual quarks and gluons flickering in and out of existence. When high-energy electrons scatter off a proton, they are not hitting static quarks sitting in fixed positions. They are interacting with this dynamic sea. The scattering patterns reveal not just the 3 valence quarks, but the gluons and C quarks surrounding them. The proton's internal structure is richer and more dynamic than the simple 3-quark picture suggests. This dynamism is relevant because it raises a question about what probing quark structure would even mean. The quarks inside a proton are not sitting still waiting to be examined. They are participating in a continuous exchange of gluons that defines the very environment they inhabit. Separating a quark from that environment to study it in isolation is not just experimentally difficult. It may be conceptually problematic in a way that has no precedent in the earlier descents through atomic structure. The experimental evidence says quarks are point-like. This is the result that comes out of deep, inelastic scattering experiments, the same class of experiment that revealed quarks in the first place. Fire electrons at protons with enough energy to resolve structures smaller than the proton itself, and the scattering patterns are consistent with the electrons hitting objects with no measurable internal structure, no size, no extent, a geometric point. But point-like in an experiment does not mean structureless in reality. It means smaller than the resolution of the instrument used to probe it. Every time this distinction has appeared in the history of physics, it has eventually resolved in the same direction. The atom was point-like to 19th century chemistry. The nucleus was point-like to Thomson. The proton was point-like until the Stanford Linear Accelerator had enough energy to resolve the quarks inside it. At each stage, point-like meant we have not yet built an instrument sensitive enough to see the structure that is there. The resolution of a scattering experiment is determined by the wavelength of the probe. Shorter wavelength means finer resolution. The wavelength of a particle is inversely proportional to its momentum. Higher momentum means shorter wavelength. It also means finer resolution. To resolve structure inside a quark, you need a probe with a wavelength smaller than the quark size, if the quark has a size, which means a probe with momentum larger than anything currently achievable. The current experimental upper bound on quark size is approximately 10 to the power of a negative 19 meters. That is 1/10,000th the size of a proton. It is the smallest scale any experiment has ever probed directly. And at that scale, quarks show no structure, no deviation from point-like behavior, no sign of constituents within. This does not mean quarks have no structure. It means that if they have structure, it is smaller than 10 to the power of negative 19 meters. The absence of evidence at the current experimental limit is not evidence of absence at smaller scales. It is a statement about where the instruments currently reach and nothing more. The history of this distinction should produce caution rather than confidence. Every previous declaration of fundamentality was made at the edge of the available experimental resolution. Every previous declaration turned out to be wrong, not because the physics was carelessly done, but because the resolution was insufficient. The electron scattering off a quark at current energies is in the same epistemic position as the electron scattering off a proton before the Stanford experiments. It sees something point-like. It cannot see whether that point-like object has internal structure at scales below its resolution. There is one difference from the previous descents that makes the quark case genuinely harder. In the earlier cases, increasing the energy of the probe was sufficient to resolve the next level of structure. Increase the energy enough and the quarks inside the proton revealed themselves. For quarks, the situation is complicated by confinement. You cannot isolate a quark to study it the way you can isolate a proton. Any attempt to probe a quark at extremely high energies occurs inside the environment of the strongly interacting composite particle the quark inhabits. The probe is not hitting a free quark. It is hitting a quark embedded in a sea of gluons and virtual quark pairs. Separating the signal of quark substructure from the noise of that environment is a theoretical and experimental challenge with no clean solution. Point-like is the current answer. It is an honest answer given the available evidence, but it carries the same qualification every previous honest answer at the edge of experimental resolution has carried. We cannot see structure here. That is not the same as there is no structure here. The difference between those two statements is the difference between the limit of our instruments and the limit of reality. And in the history of particle physics, those two limits have never yet coincided. The question, what is a quark made of, sounds like a natural continuation of the sequence that produced it. Atoms are made of nuclei and electrons. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks. So quarks are made of what? The grammar of the question is clean. The physics of answering it is not. Every previous step in that sequence had a specific structure that made the question answerable. The atom could be ionized. Electrons could be stripped from it and studied in isolation. The nucleus could be separated from its electrons. Protons could be extracted from nuclei and fired at targets. At each level, the constituents could be liberated from the composite object containing them and examined as free particles. The question, what is this made of, was answerable because the answer could, in principle, walk out of the composite object and introduce itself. Quarks cannot do this. Confinement ensures that a quark removed from a proton does not become a free quark. It becomes the endpoint of a string of gluon field energy that immediately snaps to produce a new quark-anti-quark pair. The quark is always bound, always inside something. The constituent never escapes the composite. This changes the nature of the question in a subtle but important way. When you ask what a proton is made of, the answer is 3 quarks, because 3 quarks can, in principle, be separated and identified as distinct objects. When you ask what a quark is made of, the answer cannot follow the same logic, because whatever is inside a quark, if anything is, cannot be separated and identified in the same way. The question assumes a mode of answering that the physics of the strong force may not permit. There is a deeper problem. The mass of a quark is not simply the sum of the masses of whatever is inside it. The proton has a mass of approximately 938 megaelectron volts. The 3 valence quarks inside it have masses that sum to roughly 10 megaelectron volts. The remaining 99% of the proton's mass comes from the kinetic energy of the quarks moving inside it, and the energy of the gluon field binding them. Mass emerges from the dynamics of the system, not just from the rest masses of the constituents. If quarks have constituents, the same logic applies one level deeper. The mass of whatever is inside a quark would not simply be the quark mass divided by the number of constituents. It would be some combination of constituent rest masses and binding energies and kinetic energies that could in principle be very different from the quark mass itself. This is not a technical obstacle. It is a reminder that the intuitive picture of constituents as smaller versions of the composite object they inhabit breaks down at quantum mechanical scales, where energy and mass are interchangeable and binding energies are not negligible. The question, what is a quark made of, is a legitimate scientific question, but it requires more care than the equivalent questions at higher levels of structure. It cannot be answered by the same methods. It cannot assume the same relationship between constituent and composite, and it cannot take for granted that the answer, if one exists, will resemble anything found at the levels above it. With those qualifications in place, the attempts to answer it can be examined honestly. And the first and most direct attempt is the proposal that quarks are composite objects made of smaller particles. Particles that have been given a name, even though no experiment has ever detected them. Preons. The idea that quarks have constituents is not new. It has been pursued seriously since the 1970s, when the quark model was still fresh, and the pattern of 6 quarks and 6 leptons arranged in 3 generations was already suggesting a deeper organizational principle. The motivation was pattern recognition. The periodic table of elements looked like a random collection of substances until Mendeleev organized it by atomic number and valence. The organization revealed a repeating pattern that screamed internal structure. The elements were not fundamental. They were composites of protons, neutrons, and electrons arranged in shells that produced the periodic behavior. The Standard Model has a similar feel. 6 quarks, 6 leptons, 3 generations each containing 2 quarks and 2 leptons, with the same pattern of charges repeating at higher masses. The electron, the muon, and the tau particle are identical in every property except mass. The up, charm, and top quarks are identical in every property except mass. 3 copies of the same structure at 3 different mass scales. That repetition is not what fundamental particles are expected to look like. It is what composite particles look like when the same underlying constituents combine in the same pattern at different energy levels. Preon theories propose that quarks and leptons are composed of more fundamental particles. The name preon was introduced by Jogesh Pati and Abdus Salam in 1974. Different preon models propose different numbers of preon types and different rules for how they combine. Some models require 2 types of preon, others require 3. The specific proposals vary, but the common thread is that the 3-generation structure of the Standard Model emerges naturally from a small number of truly fundamental constituents combining in different ways. The most developed preon models can reproduce the charge assignments of quarks and leptons from simpler underlying charges carried by preons. The fractional electric charges of quarks, positive 2/3 for the up quark and negative 1/3 for the down quark, emerge from combinations of preons carrying simpler charge fractions. The pattern of 3 generations emerges from different excitation states of the same preon combinations. The Standard Model's apparently arbitrary structure becomes, in these models, a natural consequence of a simpler underlying layer. This is exactly the kind of explanatory power that motivated the search for quarks in the first place. The particle zoo of the 1950s and 1960s was arbitrary and inexplicable until quarks gave it a grammar. Preon theories propose to do the same thing for the Standard Model. to replace the apparently arbitrary collection of quarks and leptons and their masses with a simpler set of constituents whose combinations generate the observed pattern. The proposal is intellectually compelling. The problem is that it runs into a wall so specific and so quantitative that it has prevented Preon theories from gaining traction despite decades of theoretical development. A wall built not from experimental refutation, but from the energy scales the physics itself demands. The wall Preon theories run into is called the compositeness scale problem. It follows directly from the uncertainty principle and from what is already known about quark behavior, and it produces a number so large it places Preon physics entirely beyond the reach of any accelerator that exists or is likely to exist within any foreseeable time frame. Here is the argument. If quarks are composite objects made of preons, then preons must be confined inside quarks. The size of that confinement determines the energy scale of the preon physics. Smaller confinement means higher energy scale. The current experimental upper bound on quark size is approximately 10 to the power of negative 19 meters. Preons must be confined within that bound, probably much smaller if they are to have avoided detection in every experiment conducted so far. The uncertainty principle connects confinement size directly to momentum. Confine something to a region of 10 to the power of negative 19 meters, and the momentum uncertainty of the confined object must be at least of order 10 to the power of negative 19 meters in natural units. Converting that momentum to an energy gives roughly 10,000 times the mass of a proton, 10,000 giga-electron volts, 10 tera-electron volts. That is the minimum energy scale at which preon physics must operate given current experimental bounds on quark size, and it is already at the edge of what the Large Hadron Collider can probe. If preons are smaller than the current bound, which they must be to have escaped detection, the energy scale is correspondingly higher. Preons confined to a region 10 times smaller require probing at energies 10 times higher. 100 times smaller requires 100 times more energy. But there is a deeper problem than just energy scale. It is called the naturalness problem of preon models. If preons are confined at 10 tera-electron volt scales, their binding energy is of that same order. The mass of the quark they produce should therefore also be of that order, but the up quark has a mass of roughly 2 mega-electron volts, not 10 tera-electron volts. The quark mass is roughly 10 million times smaller than the binding energy of its supposed constituents. This is not impossible. The proton mass is also much smaller than the energy scale of the strong force that confines its quarks. Binding energies can cancel to produce a composite mass much smaller than the individual energy scales involved, but the cancellation required for quarks is extraordinarily precise. The preon binding energies must cancel to 1 part in 10 million to produce the observed quark masses. That level of cancellation demands an explanation, a natural explanation for why the cancellation is so precise, and no preon theory has produced one that satisfies the standards of the field. This is the energy scale problem in its full form. Not just that preon physics happens at energies beyond current reach, but that producing light quarks from heavy preon constituents requires a fine-tuning so extreme it reintroduces exactly the kind of unexplained arbitrariness that preon theories were supposed to eliminate. String theory approaches the question of quark composition from a direction so different from preon theories that it barely resembles the same inquiry. Preon theories ask what smaller particles are inside a quark. They assume the next level of structure looks like the previous ones, smaller objects, bound together, producing composite behavior. The logic of Russian dolls applied one more time to the smallest doll currently known. String theory dissolves that logic entirely. In string theory, the fundamental constituents of reality are not particles at all. They are one-dimensional objects, strings, tiny loops or open segments of energy whose length is comparable to the Planck length, roughly 10 to the power of -35 meters, 20 orders of magnitude smaller than a proton, a scale so far below current experimental reach that no conceivable accelerator could probe it directly. Every particle in the Standard Model, every quark, every lepton, every force carrier is in string theory the same kind of object, a string, vibrating in a specific mode. The electron is a string vibrating one way, the up quark is a string vibrating another way. The photon is a string vibrating in a third mode. The diversity of particles is not a diversity of constituents. It is a diversity of vibrational states of a single type of object. This means a quark is not made of smaller particles in any conventional sense. It is a vibrational mode of a string. Asking what is inside a quark in string theory is like asking what is inside a musical note. The note is not a container. It is a pattern of vibration in a medium. The quark is not a container either. It is a pattern of vibration in the string. String theory has a specific answer to the mass hierarchy problem that Preon theories struggle with. Different vibrational modes of the same string naturally have different energies, and therefore different masses. The 3 generations of quarks could in principle correspond to different excitation levels of the same string. The mass differences between generations would reflect the energy differences between vibrational modes rather than requiring fine-tuned cancellations between preon-binding energies. String theory also removes the point-like singularities that appear in quantum field theory when particles are treated as geometric points. A string has a minimum length. It cannot be compressed to a point. The infinities that plague point-particle theories are softened by the extended nature of the string. In this sense, string theory does answer the question of what is inside a quark, not smaller particles, a minimum length below which the concept of internal structure in the conventional sense ceases to apply. The difficulty with string theory as an answer to quark composition is the same difficulty that haunts all of string theory. It makes no predictions that current experiments can test. The string scale is 20 orders of magnitude below current experimental reach. The extra dimensions string theory requires are curled up at scales equally inaccessible. The theory is mathematically rich and internally consistent, but its connection to observable physics remains indirect and contested. Before Preon theories, and before string theory, there was a completely different way of thinking about what particles are made of. One that rejected the question of constituents entirely, not because the question was unanswerable, but because it was asking the wrong thing. In the late 1950s and 1960s, Geoffrey Chew developed a framework called the Bootstrap theory. Its central idea was radical enough that it was called nuclear democracy. The proposal was this: no particle is more fundamental than any other. Every strongly interacting particle is a composite of every other strongly interacting particle simultaneously. The proton is made of pions. The pions are made of protons. The proton is made of protons. The structure is self-referential all the way down because there is no down, there is no bottom level, no fundamental constituents, just a self-consistent web of particles, each of which is in some sense composed of all the others. This sounds circular because it is. Deliberately so. Chew argued that the self-consistency requirement itself was powerful enough to determine the properties of all the particles. That the spectrum of strongly interacting particles was not the result of some underlying layer of more fundamental objects, but the unique self-consistent solution to the constraints imposed by quantum mechanics, special relativity, and the requirement that the scattering matrix connecting initial and final states of particle collisions be mathematically well behaved. The bootstrap was not a vague philosophical position, it was a concrete mathematical program. Chu and his collaborators derived relationships between particle masses and scattering amplitudes from self-consistency conditions alone. Some of those relationships matched experimental data remarkably well. The program produced genuine predictions and genuine successes in a domain where other approaches struggled. The quark model and eventually quantum chromodynamics displaced the bootstrap as the dominant framework for understanding strongly interacting particles. The experimental confirmation of quarks at Stanford made the constituent picture too compelling to ignore. The bootstrap's insistence that no particle was more fundamental than any other became harder to maintain when electrons were visibly bouncing off hard point-like objects inside protons. But the bootstrap left a residue that has never fully dissolved. The idea that the question of what something is made of might not always have a constituent answer, that self-consistency and symmetry might be more fundamental than any particular set of building blocks, that the demand for smaller and smaller objects at each level of structure might eventually reach a level where that demand simply does not apply. String theory has echoes of the bootstrap. The consistency requirements of string theory are extraordinarily tight. The theory works in a specific number of dimensions and not others. It requires supersymmetry. It constrains its own structure through self-consistency in a way that recalls Chu's original program. Some physicists see this as a deep connection. Others see it as a superficial resemblance between two very different mathematical frameworks. What the bootstrap contributed permanently to the question of quark composition is a reminder that constituent thinking has limits, that below some level of structure the Russian doll logic may break down, not because we lack the instruments to open the next doll, but because the next doll is not a doll at all. If direct observation of quark constituents is beyond current experimental reach, there is still something experiments can do. They can look for indirect signatures of compositeness without resolving the internal structure directly. The logic is the same one that revealed nuclear structure before anyone could image individual protons and neutrons. Before the Stanford experiments confirmed quarks directly, physicists knew something was structured inside the proton from the way particles scattered off it at unexpected angles. The internal structure left fingerprints in the scattering data, even when the structure itself could not be resolved directly. Compositeness tests look for equivalent fingerprints at the quark level. The most direct test looks for deviations from the predictions of the standard model in high-energy quark collisions. If quarks are point-like and structureless, their collisions should follow the standard model predictions exactly at all energies. If quarks have internal structure, that structure will begin to influence the collision outcomes at energies approaching the compositeness scale. The collisions will deviate from standard model predictions in specific ways. The angular distribution of collision products will change. The rate of certain processes will shift. The deviations will grow larger as the collision energy approaches the scale of the internal structure. The Large Hadron Collider has searched for exactly these deviations. Proton collisions at energies of up to 13 tera-electron-volts have been analyzed for signs of quark compositeness. The results are consistent with the standard model predictions to high precision. No deviations have been found. This sets a lower bound on the compositeness scale. If quarks have internal structure, the energy scale of that structure must be above approximately 10 tera-electron-volts, consistent with the bound from direct size measurements, and consistent with the energy scale problem that haunts Preon theories. a second class of tests looks for excited states of quarks. If a quark is a composite object, its constituents can in principle be arranged in different configurations with different energies, just as the hydrogen atom has a ground state and excited states produced by different electron configurations. A composite quark should have excited states produced by different preon configurations. Those excited states would appear as new heavy particles in collider data. Particles with the same quantum numbers as quarks but higher masses, decaying rapidly back to ordinary quarks by emitting photons or gluons. No excited quark states have been found. The absence sets further constraints on preon models. Any preon model must explain not just the ground state quarks we observe, but the absence of excited states at all masses probed so far. These negative results are not failures. They are measurements. They place the physics of quark substructure, if it exists, at a specific energy scale, and constrain the properties any viable theory must have. The constraints are tight enough that most of the preon models proposed in the 1970s and 1980s have been ruled out. What remains must be more cleverly constructed, more carefully tuned, and more carefully hidden from the experiments that have been searching for it. The Large Hadron Collider is the largest and most energetic particle accelerator ever built. A ring of superconducting magnets 27 kilometers in circumference, buried beneath the Franco-Swiss border near Geneva. It accelerates protons to within a fraction of a percent of the speed of light and collides them at energies of up to 13 tera-electron volts. The collisions briefly recreate conditions not seen in the universe since fractions of a second after the Big Bang. The detectors surrounding the collision points are among the most complex instruments ever constructed, tracking the trajectories and energies of thousands of particles produced in each collision with extraordinary precision. It has found no evidence of quark substructure, not a hint, not a suggestive deviation from standard model predictions that might warrant further investigation. The quark, at every energy scale the Large Hadron Collider can probe, behaves exactly as the standard model predicts a point-like structureless fundamental particle should behave. Every angular distribution, every production rate, every decay pattern, consistent with point-like quarks and nothing beneath them. This is a remarkable result, not because it confirms the standard model, which has been confirmed by every experiment for 50 years, but because of what it implies about where any physics beyond the standard model must be hiding. The Large Hadron Collider was designed in part to find the next layer of structure if it existed at accessible energies. It found the Higgs boson, the last missing piece of the standard model, in 2012. It has found nothing else. No preons, no excited quarks, no new strongly interacting particles that would suggest a deeper level of compositeness. The null result pushes the compositeness scale higher. Every year of data without a deviation from standard model predictions is another year of confirmation that if quarks have internal structure, it is hidden at energies higher than current experiments can reach. The lower bound on the compositeness scale moves upward with each analysis. Currently sitting above 10 tera-electron volts, it will move higher still as more data is collected and analyzed. A proposed successor to the Large Hadron Collider, called the Future Circular Collider, would operate at collision energies of 100 tera-electron volts, 10 times the current maximum. It would probe quark structure at scales 10 times smaller than current experiments reach. If preons exist at scales just above the current bound, they would appear in Future Circular Collider data as deviations from standard model predictions or as new particles in the collision debris. But the Future Circular Collider is a proposal, not a facility. Its construction would require decades and resources comparable to the largest scientific projects ever undertaken. And even if built, and even if it found no evidence of quark substructure, it would push the bound higher, but not eliminate the possibility. There is always a smaller scale, always a higher energy, always a region the current instrument cannot reach. The Large Hadron Collider has told us where quark substructure is not. It cannot tell us where it is, or whether it exists at all. That distinction between the absence of evidence at a specific scale and the absence of structure at all scales is the epistemic situation particle physics currently inhabits with respect to the interior of the quark. The experimental limits of the Large Hadron Collider are a practical barrier. Build a bigger accelerator and the barrier moves. Spend more money, wait more decades, and the accessible energy scale rises. The barrier is real, but it is in principle surmountable by the same methods that have worked at every previous level of structure. Confinement is a different kind of barrier entirely. Every previous descent through the layers of matter relied on the same basic method. Isolate the constituent, study it as a free particle, measure its properties directly. The electron was isolated from the atom and studied in vacuum. The proton was separated from the nucleus and fired at targets. The quark was inferred from scattering patterns inside the proton, but the inference was clean because the scattering resolved the quark as a distinct object with distinct properties inside a known composite. To study what is inside a quark by the same method, you would need to isolate a quark, extract it from the proton, hold it still long enough to fire something at it, with enough energy to resolve its internal structure. Confinement makes the first step of that procedure impossible in principle, rather than merely difficult in practice. A quark removed from a proton does not become a free quark. It becomes the seed of a new composite particle. The strong force will not permit the isolation that the experimental method requires. This means that even if preons exist at scales well within reach of a future accelerator, the method of probing them is fundamentally different from every previous compositeness experiment. You cannot shoot at a free quark. You can only shoot at quarks inside protons and try to distinguish the signature of preon substructure from the overwhelming background of strong force dynamics surrounding the quark you are trying to examine. That background is not a minor complication. The interior of a proton at high energies is a dense churning environment of quarks and gluons interacting continuously. Any signal from preon substructure inside a quark must be extracted from that environment. The theoretical tools required to make that extraction reliably are among the most computationally demanding in all of physics. The calculations required to predict what standard model processes look like at those energies are themselves only approximate. Distinguishing a small deviation due to preon substructure from an approximate theoretical prediction is an exercise in pushing both theory and experiment to their absolute limits simultaneously. Confinement does not make the question of quark substructure unanswerable. It makes it harder to answer than any previous compositeness question in the history of physics. The epistemic wall it creates is not absolute, but it is higher and more solid than anything the descent through atomic structure encountered on the way down to the quark. What sits on the other side of that wall, whether it is preons or strings or something currently unimagined, is the question. And the honest answer to that question requires stating precisely what current physics knows, what it suspects, and where its knowledge genuinely ends. The honest answer to the question of what a quark is made of is this: we do not know. And the not knowing is not a temporary gap awaiting the next experiment. It is a structured ignorance with precise boundaries, an ignorance that knows exactly where it begins and why it cannot yet be resolved. At every scale current experiments can reach, quarks behave as point-like structureless fundamental particles. No deviation from standard model predictions has been found. No excited quark states have appeared in collider data. No Preon signatures have emerged from any analysis of any dataset produced by any accelerator ever built. The experimental verdict at accessible energy scales is unambiguous. If quarks have internal structure, it is hidden below 10 to the power of -19 meters and above 10 tera-electron volts in energy scale. That is not nothing. It is a precise constraint. Any theory proposing quark substructure must hide its predictions below that scale and above that energy. The space of viable Preon theories has been narrowed significantly by decades of null results. What remains must be cleverly constructed, carefully tuned, and consistent with everything the standard model predicts in the energy range where the standard model has been tested. The theoretical candidates each dissolve the question differently. Preon theories answer it in the familiar way. Quarks are composite, smaller particles inside them. The three-generation structure of the standard model emerges from Preon combinations, the way the periodic table emerges from electron shell configurations. The answer is compelling in motivation and crippled in execution by the fine-tuning problem and the energy scale barrier. String theory replaces the question entirely. A quark is not a container. It is a vibrational mode of a string at the Planck scale. Asking what is inside it is like asking what is inside a note of music. The question assumes a structure the answer does not have. Internal composition in the conventional sense ends at the string. Below that, there is no below. Bootstrap theory suggests something stranger still, that the demand for constituents may itself be the wrong framework at sufficient depth. That self-consistency and symmetry may be more fundamental than any particular set of building blocks, that the Russian doll logic has a level at which it simply does not apply. None of these answers has been confirmed, none has been refuted. They exist as theoretical possibilities constrained by experiment, but not selected by it. The question remains open in the deepest sense, not open like a calculation waiting to be finished, open like a door behind which the room has not yet been built. What the descent through matter has established is a pattern and a limit. The pattern is that every level of apparent fundamentality has concealed a deeper one. The limit is that the tools used to find each deeper level become harder to build and harder to interpret at every step down. The quark is where that pattern meets that limit most sharply, where the experimental method that worked from atom to nucleus to proton to quark runs into confinement on one side and energy scale on the other. Whether the pattern continues below the quark is the question. Current physics cannot answer it. What it can say is that the question is real, the constraints are precise, and the answer when it comes will require either a new accelerator of almost unimaginable scale, a new theoretical framework that extracts information from confinement in ways not yet conceived, or both. The quark may be the bottom, or it may be the deepest basement current physics can reach with its current tools. Those are not the same statement, and the difference between them is where the next chapter of this descent begins.